Okay, good morning. So we come to the last lecture this semester, and it's a lie to say basically the semester passed by very quickly. It did not. It was very slow at sometimes, but it's really good so far. Okay, so I don't know. I'm not sure how many of you in the room have the final exam by Friday, but for everybody else, I think you are done, right? Almost. So we are grading. So today I really wanted to kind of share. I have a lot of things to cover, but I don't think I will be able to cover everything in detail. I just want to share with you these kind of recent topics that's really at the core of the machine learning. What happens if you don't have labeled data, right? So not always you have, like in computer vision, it's very easy, right? To get people to label your data, but not in that application. So we'll see basically how different ways how you can do that. Okay. So this is kind of a typical supervised deep learning. We have seen this quite often, where at the end of the day, when you're really back propagating, you already have this kind of one hot ground truth label. This is really coming from the annotations, right? So basically this image at the input has this class, then you look at the difference, and then back propagate the loss, and so on, right? So that's basically what the typical one. So the question is, what really happens if you really don't have such a ground truth, or you don't have many? So you cannot really train very well. So let's look at some kind of the main reasons why we may not really have fully labeled data, right? And we can really split these into, 3 different categories, but these are kind of the primary ones, but there are many other reasons. So the first one is really the expensive, the expensive labeling process, either in terms of cost or time, and I will share this more detail about this in a minute. And then the second one is in some applications, like a medical field, for example, you need really a trained expert, right? Which is not really very easy to get. And then, of course, we have all the privacy and security problems. So if you look at the cost in here, this is just the annotation business or global market. They expected by 2028 to be above $10 billion, right? Just annotation, just to have these kind of annotation companies. There are many of them all around. You can. In the medical field, we have reading centers, especially these are reading centers. They take the CT scan, stuff like this. They read it and they give you a report. That's called reading centers, right? And now they are kind of more and more, tilting toward becoming annotation centers or annotation businesses. And those basically are people who have their own AI tool to label data, right? So they build their own AI tool to label data. So it's not necessarily mean that they are really doing it by human for the whole thing, right? So there's whenever you really in your career, if you come up with a decision to hire such annotation companies, my advice is to dig deep in how they do it, because there's a lot of tricks they play, right? And we have been working with a couple of them for the last 3-4 years, and we are still discovering some insights. But it's a very big business. So. And we say, okay, yeah, the cost, especially they will really charge you maybe a leg to get your data annotated, even for computer vision applications. But still, it's very expensive. So if you look at the life cycle, and this is something being updated, but there is an agreed upon pie chart, right? If you look at the whole AI end-to-end at the model, right? What are the different components, right? So you have your data, you have to clean it up a little bit, right? First of all, you have to have your sensor. You have to have identification of the data. We have, for example, now a project with AWS, and we are just in the process for the last 4 months just to do this data identification and data aggregation. We haven't even started, collecting data. And then after that, you have to really spend quite a bit of time on cleaning the data, then annotation and labeling the data, do some augmentation, and then basically what we learned this semester starts, right? Basically the algorithms, the training, the tuning, the generalization, all this kind of, and deployment applications. So you can see that's really a small part compared to preparing your data to be really trained upon, right? And that's really kind of, doesn't matter what application you are thinking of, it's almost always the case. I mean, in the medical field, for example, this becomes really much bigger, right? In the medical, like the medical imaging side of things, geophysics, for example, because there is quite a bit of process to get the data. In the computer vision, it's a little bit more straightforward, but still, it really consumes the majority of the time that you need to do this. So we have this kind of a project with Ford Motor Company for the last, and Waymo. Waymo is a spin-off from Ford for the last couple of years, where we really had to work with the annotation companies to really annotate certain videos. And you can see from these annotations, we have 3D bounding boxes, right? So we have a depth component in these bounding boxes, right? So this is just one example from their annotation, and their annotation companies basically this is third party. Certain part they have an AI model, but certain part didn't have an AI model. So, but everything in here, if you just look at just one data point, like about this video in here is roughly, I think, a 1 minute video. I think, yeah, so 578 frames. So this is really nothing, nothing, huge. They spend 1 day, right, roughly, right? This is including initial labeling, verification, going back, go through data quality control, the whole thing until we really get it. So from our data, which is very, very huge video data that was collected on the streets in, I think, Michigan, Chicago, and California. They have their vans just driving around and parked in certain areas and on these cities or states. And I think they collectively, it's a huge amount of money they spent to annotate that data. And the idea is how we can really reduce that. So if you look at really people, if you look at the literature, like active learning, we studied active learning like in one of the lectures, right? Ryan talked about active learning. Active learning, basically, you have to make a decision to say, yeah, maybe this one we need a human to label it, but we need to pick which one to get labeled by a human, right? That's basically the decision. If you look at all the active learning literature in the last 15 years, they look at basically the number of these data samples, like how many frames I need to label, that's my cost, right? But what we found from this experiment, that really varies quite a bit. It's not really very uniform. So the time that you take to label just one frame can vary quite a bit from one video to another video, or from one sitting to another sitting, because there might be some distortion, there might be some occlusion, there might be a lot of different things, and the variation is really very huge. So a more accurate, basically, kind of a cost is really to have not only the number but also the time, like literally the time that it takes to label these data sample. And once we factor that in, we get a much better improvement in the active learning actually quality. And hopefully this data set will be released before the end of the year by Ford to the public. But it's really very eye-opening to say cost is not really the number of samples, the cost is really how much it takes you really to sample these. And now with the annotation companies, they can log their time accordingly here, which is really very interesting. You will see when you take the log from these companies, when you just process it, you will find some outliers, and it turned out that some of their employees basically don't factor in their bathroom breaks into the labeling. So we had to go back and remove these outliers because you cannot, cannot like take maybe 15 minutes to label basically 2 bounding boxes. It didn't make much sense. So we cleaned that up, and hopefully it will see the light before the end of the year and this data set. Anyway, so the second major component is really kind of applications where you need really a domain expert. Like Mechanical Turk is you can access 8 billion people around the world, right? I mean, it's and they yes. I don't know if you're discussing. You talked about earlier, AI. When obviously having labeled data is optimal. So if you receive data, you use the trend sort of network, and do people normally verify the data is directly labeled? It's not, and it's like dangerous, or it could be dangerous. Like I think it might not be about it can get this. Absolutely, yes. So so these annotation companies, is part of their kind of what you sign up the contract with them, there is a quality control at the end, right? And that is basically where they do the verification, right? And that usually you insert what you are looking for exactly in that quality control. Even with that, you don't really get 100% accuracy in the labeling. You'll get still 97, 90, even lower actually percentage of this accuracy. So you have some mislabels for sure. There is no question about it, right? And that's really part of the danger in just relying completely on the output from these, because that 3% could be could be really problematic for a safety application, right? So that's why there is quite a bit of applications where, like anomaly detection, outliers, discovery, to kind of have this kind of control, trust in the network, right? What Mohit talked about, explainability, what we didn't really have time to talk about, the whole thing about trust in AI, right? How do you trust the AI model? And what are the different metrics you can really come up with? You can really trust that AI model, which takes into consideration the labels themselves, how much confidence you have in the labels, right? The data, the labels, and then you have the model itself, right? So, but absolutely, that's an extremely important part of this process. I mean, even for the application like medical field, right? I mean, medical field, I mean, and even the geophysics and medical field, I mean, they're really very, I mean, there's quite a bit of analogies between them because the human is extremely centric to these applications. There is, otherwise it will become a little bit of a guess. I mean, I don't think any patient would like to rely on AI alone, right? And I don't think any patient would like to rely on the doctor alone anymore, because you want to get basically both of these, and that's what really happens. The doctor at the end of the day will have the AI output, look at it, and then just make a decision. We had this project with a clinic in Texas and Houston, and basically, they gave us some data, and it's clinical trial data, and my students had to really kind of process this data and try to see what based on the classification that they gave us. So, in one of the updates, basically the students said somehow the AI picked up something, but you completely didn't really label this with anything. They came back to us and they said actually the AI was more correct than the human because they completely missed it in their clinical trial. So they had to repeat basically quite a bit of the experiments just because of that. So that happens. Human error is there as well, right? But in all of these, basically, if you really want to get a human to sit down as a doctor, that's extremely expensive, right? Mechanical Turk, you can pay people like, like, I don't know, 2 cents a frame, right? Or 2 cents for a bounding box around the world. And you will find, I don't know, like, 10,000 people doing that and are willing to do that, right? But you cannot find a doctor to pay him, 2 cents a bounding box, right? So I rather have them in the operating room, not labeling. Same thing with geophysics. The geophysics, I mean, there is a saying basically when you have 2 geophysicists in the same room, you will have 3 opinions, right? They will never agree. So that's another problem, right? And you see that in, like in doctor or medical field, there is an agreement is one thing, same thing in geophysics, but also there is the cost. So all of these basically are really very, very expensive application to get some real labels to your data. And of course, we have the privacy issues, right? We have quite a bit of privacy. And you saw the news, basically, Samsung employees using ChatGPT, and they revealed some of their secrets, right? Through ChatGPT. So there's quite a bit of problem when it comes to security on this label data, and they're not really straightforward, quite frankly, from our own experience. Okay. So these are kind of the major problems. How can we really mimic? How can we come up with a new kind of paradigms that will enable us to not rely only on the fully labeled data? So there are some other paradigms. We call them semi-supervised, weakly supervised, and self-supervised. Weakly supervised, this was like 7 years old kind of name, but now it's called self-supervised, and we'll hopefully see the difference between them. But they are really the technical, center of it, they are really very similar in that sense. The self-supervised, basically, you have much less labeled data, meaning almost you don't have labeled data, almost unsupervised, but you can really get some kind of initiation. So in the weakly supervised, you have some data that's really partially annotated. The difference between these two, in the weakly supervised and the semi-supervised. In the weakly supervised, for example, you want to do segmentation, and we'll see an example. You want to do a pixel classification, right? But you cannot really access annotation to the pixel segmentation. So you have image classification. So you start with a different kind of label, and from there you have to map it to some other label, right? The label domain. In the semi-supervised, you will have exactly what you are looking for, but very, very few of them, right? So that's where fine-tuning and things like that come into the picture. Okay, so I want to use basically some of our recent work, not really recent, it's almost like 4 years old, on the weakly supervised work. And I want to use the geophysics. So in the geophysics, imagine this is a subsurface image from the North Sea, and we have this input in here. And then we know if you give this to a geophysicist, they will understand basically this is a salt dome, where basically you have some kind of pockets of fossil oil. or gas. I think this is oil mainly in the North Sea. Anyway, so you have structures. You have the north, you have the salt dome, and then you have some others. So if you really have a binary classification, you want to come up with this kind of segmentation. You want to say this is one class and this is another class, right? At the pixel level, right? You want to have this machine learning model in here as an example. So these ones in here, if you really have access to this pixel level labels, the ones on the left-hand side, then basically that's great. But you can really train with these fully supervised and you are good to go. We call these strong labels because really exactly what you are looking for in here. But usually what you have from the geophysicists, they have some kind of partial annotation, like something like this, where they have just a brush to say, okay, this area belongs to one class, this is another class, because they cannot really go and at the pixel level give you these annotations, for example. Or they give you a bounding box like that, or they give you a whole image level label, right? So all of these we refer to as weak labels. For example, this one is really kind of not as weak as the other two, because there's a bounding box exactly where the salt dome is. But basically, it's all of them are not really as strong as this pixel level labels, for example. So now imagine that we have these image level labels, right? We have labels for the image level. How can we do that? So this is an end-to-end methodology. It's an illustration from my former students, where you input, basically you have to come up with your training data because you don't have that data. So you have to create your own training data that have, you automatically generated the labels, but there is quite a bit of error in these labels, right? And that's fine. We will live with that. And then he has a network architecture, and then he has some kind of loss function to take into account the mislabels that we already created in the first step. Let's look at the first one. How can we get training data? So the first thing, basically, what you could do is to have exemplars from each one of the classes. So imagine that we have 4 classes, right? And then we will give basically 4 exemplars to our human being, and then the geophysicist will sit down and label these. Basically, that's what this means. The human only gave you one example from each one of those classes. That's all what they did, and that's the input, right? So that's all what you have asked them to do. So they can do that basically in less than half an hour, right? From all the data, it's very easy to give you example, just one example from each, right? The more, just remember this for later on, the more examples you have from the geophysicist, the better your method will look, like accuracy-wise. So what you could do with that, you start to come up with a similarity metric, right? You want to have a retrieval problem. So you have a retrieval step where you access the entire data set that you have, or database that you have. And then you start to have similarity, meaning that the first exemplar in here, like for example, this is kind of a chaotic structure. I want to have all the ones that I have in my data set that really looks similar to this structure. Another one, another class, another class, another class. So now you have what? You created how many? Thousands of these image labels. You understand that? Does this make sense? Okay. So you went from 4 labels from a human to thousands for each one of them using some kind of a similarity metric. Is this perfect? Far from it, right? I teach image processing in the fall semester, and then we spend, like, one of the 4 chapters we spend quite a bit is this topic in here. How do you incorporate the human vision system into coming up with similarity and equality metric for visual data? And is not very highly accurate, but it especially for this application, you can see is very noisy, artifacts in the data. So what is similar, right? It's very, very tough. But nevertheless, you have something that you can start with in here, right? So now, once you have these weak labels, because the application at the end of the day is localization. You want to go to exactly the location of each one of those structures, either salt dome, fault, chaotic structure, or horizon, and so on. So you have to come up with this kind of a weakly supervised label mapping. So this really map. So if I have this image in here, I have this label for it. I want to map this to become at the pixel level, right? So basically, where exactly which pixel belong to this class, which ones don't belong to this class, right? And that's basically where the weakly supervised labeling come into the picture. So the more details actually we have in this physics paper, and in his this is the student, his dissertation in the Georgia Tech Library has all the the math derivations if you're interested in applying this method to your own research. So this is the similarity retrieval, kind of a very, very typical. You have your exemplars from the geophysicists, like 4 of them. you create some kind of, you extract some features. You can really do this using classical algorithms, or you can use autoencoders or some other application. And then you have your dataset. You extract the same features and you start to build some kind of similarity comparison between them. And I had a kind of two students in the past who really come with quite a bit of similarity methods when you have computational images like this, when you have quite a bit of, if you look at this data, it's very different from our natural image. Natural image, we have color, right? We have boundary between the objects, right? All of this gives you quite a bit of information. We have a depth component, right? We don't have any of this in here. We don't have color. We don't really have object boundaries. It's a totally different set of data that you have to deal with to create the new similarity, because we as a human, basically, now we will disagree where is the boundary, right, between these two. So you want to take that confidence into account in your similarity comparison methods. Anyway, so you come with this kind of structure, and then after that, you want to input basically these images, for example, right, and then you want to map them to this segmentation, meaning that what I have in here, basically in this cyan color in here, that means this pixel in here is a chaotic, belongs to the chaotic structure, which is what we have in here, right? You can see there is some outliers, like this is wrong, right? You can easily say this is wrong. This one here, for example, I have these two chaotic structures, so this is correct. This one here, for example, is a mistake, right? This one here, this one here is also a mistake, for example. This one, basically all the other class. That means I don't really have a fault, a chaotic, or a salt dome in this structure. You want that too as well. This is kind of the null class. These are the faults. The faults are really 1 pixel lines. So it's basically what you could do in here, just an area, right? So you really download, you narrow down your area of what the faults are to this very, very small area, right? And you can see this is even better job in here. And the salt dome is the only salt dome boundaries, right? So you can really see this is very, very well done actually in here. This is the salt dome boundary. And you can see not only one, but also this one here. So this whole variation here, which can be a few kilometers, is basically kind of where people disagree between them. But nevertheless, you want to create this label, and then you can now use these labels to train your model. And now, the question you ask, you can see we have a lot of errors, right? We have these errors in here already in place in these labels. They are really not as good as when you have a human, but you have many of them, right? So the numbers in here really help you quite a bit because you have a lot of these. So what the output from here, you will have the original image, you will have the pixel level labels, and then what you have, which is really a side product from this methodology in here. Where is this? This methodology in here is the confidence level. So basically, you will have an output to saying, this pixel, it has this label, and I have this much confidence in my label, right? So that you don't really have from the human labeling, right? You cannot really have it from the human labeling, or you could, but it will be a little bit expensive to get. So each one of those pixels in here, it has a corresponding, confidence value, right? And now you can really start to imagine we can use that into training the model in here. Okay, so this database, we'll skip this one. Okay, so this is basically how the weakly supervised will look like. You have this whole cross section. From this cross section, you can see there is a salt dome in here. There are some faults in here. There is a fault. It should be somewhere here. Yeah, maybe somewhere here. There's some fault in here. There's a chaotic structure here, and then everything else just other. Although we could really do chimney, we do horizon, but we are not doing that in here. And then what you want to get output from this one is this, right? This is what your output would look like, right? And then if you want to compare it with the human labeled one, is this is the ground truth, right? So you can see from here, we got really more or less the fault correctly, the salt dome more or less correctly, the chaotic structure correctly, but we have some really false positives in here, and also we have a false negative, which is really the fault that we really completely missed here, right? But this example is very good because even the human label missed the fault. So now when you compare that, the algorithm missed the fault, the human actually missed the fault, but there is a fault, right, in here. So it's because it's very, very tough fault actually to label, to find. Anyway, so how can we go from here to there, right? And there are really many different methods. I just want to share basically one it's beautiful because it has to do with the component or part-based transformation. So if you look at the PCA, if you have face images and look at the PCA components, the first component like a DC in DCT or phase transform, it has the major components, and then you have all the details in the remaining components. The same thing for vector quantization. You have each one of them basically is almost everything, each part of the face is in every vector quantization component, right? But if you look at the first one, which is basically is the part-based. Part-based meaning each one of your components is really capturing certain part from the face. Like one of them will have the eye, you have the nose, you have the mouth, you have, so each one of them is only for a certain part. We call them parts-based transformation. And this one here is what we refer to as non-negative matrix factorization, NMF, which is the same one we have in here. Is one of the most effective ones. And the idea in here is you want to really approximate your data with these two matrices, right? So one of them has the weights, the other one has the membership, meaning that one of them has the features. So you create the features, and the other one has membership, like how much this image has membership in each one of these features. But you're not creating any of them from anywhere. You are really you're generating this on the go, right? So usually what you will have this as a non-negative. That's why we had W and H are 0 or positive, and then you are really minimizing the mean square error, and that's really the typical NMF framework. What my student did really kind of is if you do it, it not really work very well. Straightforward on the geophysics application. So what he did, this is the formulation. You need to kind of to manage or control the magnitudes of your features as well as the membership, but also he want to make it basically orthogonal to each other, right? This orthogonality is extremely important, as I will see you. I will show you in a minute. And then also he added this sparsity. He wants them to be as sparse as possible in here. So if you look on the left-hand side, if I have my H, basically what I have each sample, each image in the x-axis. I have my features basically on the y-axis, right? So now each sample in here has all these features in here, right? So if you do that without any orthogonality, term, if you look at here, you can see there's a block, right? You can see there is some dots in here highlighted. You can imagine this is one class, this is another class, this is the third class, this is the fourth class. So, right, they are really organized that way. But the problem on the left-hand side, that basically the membership to the other classes also are there, not really 0. You can see that in here. You have quite a bit of membership. These features for one class, these features for another class, these features for a third class, and this feature for the fourth class. If you take this image in here, which belongs to this class in here, it has a lot of non-zero components in the other features. And that's a problem, right? So when we did the orthogonality, then we have the one on the right-hand side. We added this orthogonality on the edge axis. So what that means, now I zeroed out quite a bit of these ones. Not all of them completely, but I have zeroed out almost every, and I still have this one. But in here, for example, it's almost 0. This is almost, everything is 0. So for these images, right, they are really completely represented by these features, right? And they still have few a little bit from the other features. So this, especially these two classes have something in common between them. That's like, for example, look in here, this one here, it has also non-zero components in here. Do you get this point? Any question? Does this make sense? This confusion matrix. Okay. So what you do basically, start to, you just, I will not talk much about the k-mean. This is just initialization. All the idea of the k-means, you start basically just, you want to initialize your edge matrix in here. And that's all what you want to, so that's where the membership matrix. And then your features are the W's. So his thesis, he has a very long derivation. It's not really difficult, but it's really very long derivation, where now your update from one iteration to the other in the gradient descent is nothing but a multiplier. You see, this is the way it's at t is nothing but really you have a multiplier. So you have t minus 1 times t minus, so everything is really multiplied. So the conversion actually became extremely fast in that sense, and that's really very good. He just changed a little bit in the math and makes it multiplier, not additive, and that really was a very good contribution from his side. So once you are done, then you have the entire volume. Each section is an image. You have the entire labels. You have the whole labels basically of the entire volume that you have so every voxel tell you I belong to this image and this class. Right? So every one of them. If you take sections from them, you will have this one here. So this is the basic chaotic structure. This is the faults, and then you have the salt dome. And you can see we have some kind of false positives in here, but that's fine. What he did also is the median filtering, because that's just to smooth things out and the output here, to fill in the gaps between them. I think this is a video. Let's see. Yeah, this is the chaotic structure. You can see there are some false positives. This is the faults. You can see the fault much clearer now. These are all faults, right? This one here. False, but we have discontinuity in the subsurface, right? That's basically where you have pockets from oil or gas happening. So you can see we highlighted most of them basically very well in this case. Salt dome as well, and I think this one show you the progress as you do the gradient descent updates, how you start from initialization and then you convert this to the chaotic structure. That's when you stop your optimization. Same thing for the negative class. This is the other class, right? The faults. Because when you start with it's just a k-mean cluster, it means every single image in here has the 4 clusters. That's why you start with all the colors, and then as you really progress, you really eliminate these from existence. Okay. And there's no deep network whatsoever. It just basically just solving that gradient, this optimization using gradient descent method. This one here. Okay. So now once we have that, then he did a little bit of augmentation. I think the only thing that he could do, given the nature of the data, horizontal flipping and rotation by 15 degrees. Although I heard from geophysicists this is not really acceptable because it's 15 degrees is quite a bit of degree, which I agree with. Maybe 5 is a good alternative. Anyway, so now what he has huge amount of data. He has a huge amount of labels. They are not very good labels, not very 100% accurate labels. There's a lot of errors in them, but he has the confidence, and he has the confidence value for every single label of them. So now he went ahead and started to, train this fully connected, layer, which is really very simple network, right? So the encoder decoder, we have seen this before, and now I'll just skip this. Now, the challenge in here, what will be your loss function, right? So the loss function, if you use the cross entropy as it is, then basically things will work in a way. But I showed you this focal loss before, right? And the focal loss, basically the ones he did, is actually he changed it to incorporate basically the confidence, right? So now the confidence is really incorporated in here to say basically, you remember when we had the imbalance data, we said for the least representative class, you really increase basically the contribution, the loss function and the focal loss, right? And here the same thing. If I have less confidence, right, then I will reduce basically the contribution, the loss function, right? So depending on the loss function I have. So now the network, actually, if you look at the network, the network will have to, the loss function as you back propagate, it has taken into consideration the learning rate of the network as well as the confidence of the labels, right? So the network is learning this quite a bit, but the confidence is very low. It will not be incorporated into the back propagation as much as the other ones, right? So that basically has a trade-off between the two in here. And actually, that's when if you just use the cross entropy, didn't really work because you have quite a bit of misleading labels in the data. But once you incorporate that using the focal loss, you have the confidence as part of your back propagation, things start really to work very well in here. So this is one cross section from the North Sea, and then if you look at this is the chaotic structure. So basically all of this, and this is very impressive because you remember you started with only one sample, a 25 by 25 pixel of the chaotic structure, and you managed basically to pinpoint exactly which pixels belong to the chaotic structure in this whole. Remember, each pixel here is 25 by 25 kilometer, plus or minus. And then this is basically as you go through the whole volume, which is 700 of these, 700 times 25 kilometers. I don't know how far is that, but this basically throughout the whole volume subsurface under the North Sea in here. And you can see it's really very impressive. It didn't really have a lot of false positives. Like you have a few of them in here, you have a few of them in here, right? This is where you have a fault, right? But other than that, it's really pinpointing exactly where the structure is. Same thing in here. You can repeat the same thing, but now for a fault. When you see the fault region here, we have this fault. You see this fault in here? As if you are driving into the subsurface, like as you're driving underground in the North Sea, and basically the fault will show up, the salt dome will show up, the faults will always be there, but they change in their magnitude, right? And really did a very good job basically in picking these. And all of this started with only one 25 by 25 pixel image from a human being. Everything else is automated, right? Everything else is automated in here. And that's basically where it's, he did some experiments where he added like 10 more from the human, and the accuracy just jumped quite a bit. So I think in his thesis, he had some kind of a theoretical bounds on how many, and I think in this case, seven examples were more than enough to get really very, very high accuracy, if I remember the number correctly. But that's changed from one location to another location. Same thing in here, but now for the salt dome. Imagine you are driving under the North Sea, and this you are really coming up with these salt domes, right? So you can see that's why it's keep moving, because we are moving into the volume. The second salt dome is showing up now at the end, and then the third one. There are 3 salt domes, I believe, in that volume, and this is basically a 3D view of how it will look like. Any question about this weekly supervised? Any? Okay, there's no homework on this, so that's why it's sure. Okay, so the next one is to move to self-supervised, right? And then self-supervised is just the renaming of really unsupervised learning, right? Where in fully supervised, you have the label, you have the data, you have the labels, and then you really get your predictions. You have a loss function, you backpropagate that, and so on. In the unlabeled, basically, a data set, you have only the X, you don't have the Y, and you try to kind of usually reconstruct your X, like using an autoencoder. You have X hat, and that's basically what the best you could do in many cases. In the self-supervised, basically, you start with your data, but you start to kind of map this into what we call a pretext task. We call it a pretext task into some kind of the X plus the latent space, right? And then from there, basically, you start to kind of regenerate that or reconstruct the latent space in here. And that's basically what will give you these labels. Okay. So how is this different from others? So if you look at the autoencoder, is really input the image, reconstruct the input or the input. There's no pretext task whatsoever, right? In here. Clustering is completely guided. We have no pretext task in here, and we don't really need deep learning to do that to start with. So really, why people really call it self-supervised, this function or this step early on, we refer to as a pretext task, and you'll see where it's quite a bit common between what we refer to weakly supervised and self-supervised come into the picture in this pretext task. It depends on what your task is in this step. So if you look at the self-supervised method, there are really 4 major steps, could be 5. The first one, you start with the unlabeled data, and then basically you have some labeled data. So you generate basically exactly what we had in the weakly supervised. Is not necessary in the self-supervised, but will be very helpful if you have some examples of your labeled data, right? So you start to have these 2 pairs in here. The second step where you have the pretext task involved. So you have the unlabeled data, and then you have your pretext tasks, and we'll look at some examples in a minute. You get some kind of an intermediate label, and you can imagine our weakly supervised when we created the images, the image labels. That's an intermediate one, right? That's a very similar to the weakly supervised. But you have what they refer to as a pseudo label data in between. We refer to it as the Z function. In the third step in here, you start to have a network. You use this pseudo label because you have the X's, right? And you have their corresponding pseudo labels, right? Now you have basically, you can really train a network. You train this network to regenerate basically these labels, like the Z hats. And then you have this kind of you converge, you have now a model we call edge theta, right? The fourth step is really to append another model to this edge. So what we have in here, in this step in here, we have a lot of this data, right? We have a huge amount of data, right? But in this step, we are relying on the very few label data. So you can think of this as what? This is the deep network basically training. This one is what? Fine tuning, right? This is exactly fine tuning, right? I mean, that's one way to look at this. In fine tuning, what we did, you go to the final few layers and then you fine tune them. That's why we don't refer to this as fine tuning. In here, you keep this as it is, right? You could update it. That's why we had updated in a parentheses. But the most common practice is to keep this as it is from this step. And then you have another network in here that you really completely train this one on the label data. Clearly, this one is much shallower than this one, right? Because in here you have a lot of data. In here you don't have much of label data in here. So now the output from this here is your ground truth predictions, right? You're really what you're after. You're not looking at the Z anymore, the pseudo labels. You're looking at the ground truth, the final ground truth in here. Any question about these 4 steps? Self-supervised. Are they clear? Okay. So now, what are different, basically, pretext tasks? We have transformation prediction, we have mask prediction, we have deep clustering, and then we have contrastive learning. And we'll just very quickly have examples for each one. So in a transformation prediction example, these are some examples from the literature where, for example, your pseudo labels are really how much rotation I have to the image, right? So your prediction is in the step number 3, what you're doing in here is basically how much rotation I have to the image. So you take the image, you rotate it, so now you have pseudo labels, right? Because you know exactly how much rotation you did. And then can your network, can the edge in here, this edge can predict the rotation angles, right? That becomes the task, the pretext task. And then the second example in here is basically the angle between them, right? Between the different images in here. This one here is basically kind of just add some kind of linearity to the process. So all of these, you make up the labels and you say, oh, let me make the edge predict that label, and so on. Yeah, let me go through this one. This one is like a mask prediction. Basically, you mask it because you already have the image. You mask it instead of say, can the image really predict the mask region, right? That becomes your pseudo label, right? Or intermediate label. In the clustering, basically, you have a deep clustering, which is kind of self-explainable in this case. The problem with all of these, basically, let me go back here. Yeah, here. None of them really even come close to the fully supervised. Like all these methods, they are not like this masking one, this one here, all of these, even deep clustering. None of these methods really came even close to the fully supervised, and that's why basically this area kind of took a little bit of slow down a little bit until we had this contrastive learning. SimCLR is kind of very famous for contrastive learning. It gave us quite a bit of performance boost when you have self-supervised. So if you look in here, this is the number of parameters on the x-axis. This is the ImageNet Tab 1 accuracy percentage, right? The self-supervised, right, the fully supervised is up here, right? You have very high accuracy, but also you have very few number of parameters, right? All these are the other methods in the literature. The SimCLR basically over time it got to this point, so it's very close in terms of accuracy, and in terms of parameter, basically is small. As you increase the complexity of the SimCLR twice or 4 times, you get really as very comparable performance, but the number of parameters is really huge, right? I mean, in comparison, right? So this will give quite a bit of really hope that self-supervised can really help quite a bit in this domain compared to the other 3 pretext tasks in here, right? So what is contrastive learning? Any question about this? Okay. Contrastive learning the idea is very simple. You're saying, I have this image in here, right? And I have these images in here as an example. It can be applied for any other data modality. And but the original paper really on images. And you start to say, I already want to ask myself the following question: which of these images, right, among the ones on the right hand side, are the most closely ones to the image on the left hand side? Right, I want to pick the one that's closest to it, right? So now, from these four in here, I will pick basically this cat in here to be the closest one, right? So now I have started to have what contrasted, meaning that this image and this image are a good pair, but this image and the other three should not be in the same class. So I'm starting to build this kind of, pairs in my data, right? I keep doing that basically, and then now I start to have this kind of binary decision to make, to say, are they similar or are they different from each other? And that's basically what the whole basically self-supervised using contrastive learning is all about. There are a lot of details I will not really go through, but the whole idea is you come with these examples. You need to come with the methodology to really create these pairs. And then while you're doing that, you need to come with the quantification to how similar they are. And this similarity in the representation space, not in the image space. That's very, very important, right? We will look at, when I teach in the fall, I look at difference between the image space and the representation space. Can give you completely misleading answer if you use the image space. So this is happening in the representation space, as we saw in the lecture before. So what really people do in the same CLR, this is kind of exactly what the paper was doing. You generate basically similar pairs in a like a starting batch, right? And then you augment each one of these images. For example, you take this original image, you do some augmentation, you remove the background, for example, you do some rotation, you do some kind of flipping, right? So you create all kinds of different annotation, right? And now you start to have what? I have two patches. I have the cat and I have the elephant one, right? And the batch size in here is 2, right? I do this different augmentation. And now I have these two pairs. So this is pair 1. I have these two pairs in here. This is pair 2, right? So now what the output from this very simple toy example is that every image now has a similar pair that is a transformation of the original one, right? So now you say, okay, I have these pairs. So you created these pairs in here. Remember when we were talking earlier, basically you have the mask, like they have the mask on top of the image, and it's the same process. But now the process that you are really generating is pairs. You want to create basically this kind of like similar or not similar, right? That's what you are trying to do, or a distance, right? That's why we call it contrastive learning in this case. And then once you do that, then you pass this image and the generated pairs into an encoder, right? So basically what you are doing, you are trying to create a low dimensional representation for each one of those pair images or images in this pair, right? And the third step is to further compress your representation space by doing some kind of projection to get really kind of a latent representation or embedding for each one of these images. So you have Z1 for this cat, Z2 for the other cat, Z3 for this elephant, Z4 for this zoomed in elephant head in here, for example. So now you have this kind of a embedding for each one of those images in your pair of this toy example. I mean, this is just a very simple toy example. Usually you have quite a bit of number of patches, not only 2. Now, that's what you have done here in the previous step. Now, step 4 is start to really kind of build the similarity between the two images, but not in the image space. You want to do it using the representation space. You want to look at Z1 or ZI and ZJ, right? So all the different pairs. So I have Z1 with Z2, Z1 with Z3, Z1 with Z4, Z2 with Z3, and so on. So you have a similarity across all of them. What is being used, and so far is really kind of the most effective one, is cosine similarity. And we have seen this before in the semester using cosine similarity. So cosine similarity will give you the difference, how similar these images are in the representation space, in the embedding space, right? And then once you have that, then you have this what we refer to as contrastive loss function. In the contrastive loss function, what you have on the numerator here is nothing but what you can see in here. You have what the similar pairs, right? In the denominator, you have everything else, right? Denominator, you have the similar pair, right? You have also the different pairs, like between the elephant and, because that will make this what very large. This will make what very large, right? So now that's basically the loss function here. So now you have In the numerator, the similar pairs, and then in the denominator, you have everything. Then you can compute the loss for all the different pairs that you have in your batch. So in this case, in this toy example, we have in the numerator in here, I have the loss function between these two pairs, right? Plus I have these two pairs plus these two pairs, and divide by the total number I have in here, which is 4 of them in here, because I have 2 images, I have 2 batches. I have two augmentations, so 2 times 2. And that's will be the average this, and then I get basically the complete the overall loss I have in here. I backpropagate basically that, and then I just do fine tuning at the end in here, and then I have my business space at the output. Any question about this process? So if you look at the details of self-supervised, is nothing new compared to what you have learned in this semester. How you put them together is really the part, but it's a very, very effective methodology to do that. So everything together, this is the pseudocode. You create some pairs, right, in a starting batch by augmenting each image. So what is you have an image of a cat, you augment it, now you have a pair, right? You have an image of at the very beginning, you don't know this. You don't know this is a cat, this is an elephant. You take each image, you do augmentation, but now you have a pair because one was generated from the other, right? So this is a pair. This is a good pair, right? And the assumption you start with is that image number 1, I have those 2 pairs, right? Or this pair is different from the next one, although maybe they're very similar. Could be 2 cats, right? But you at the very beginning, so these are different from each other. So I have these different patches. As you are really generating this loss function back propagating, that will start to be corrected as you are learning and training your model. So you pass these images and generate basically kind of this low dimension space, and then you really fine tune it a little bit to create this embedding, Z1 and Z2 and Z3, Z4 in this case. Those ones are being used to create the cosine similarity and back propagate the loss for all the pairs, and then you keep doing that basically until you converge. So now this is where contrastive learning, basically you have the similar pairs, we call them positive, this similar we call them negative, right? And these are many different ways basically how people really define them, right? So if you look at this is basically the description. These are different papers until like 2021. I don't think we included anything recently, but just what each one of the application, what they're really doing, what are the definition of these different similarity. So you could use what Mohit was describing. He didn't really mention this in detail in the explainable AI. He could do YP rather than a Q, for example. He could replace that, and he did that. Actually, replace that with a contrastive element from it. So if you think about YP rather than Q, that's contrastive, right? That's exactly contrastive, right? So he could replug in that into this framework as is actually, it works. Method-wise, sorry, performance-wise, as I mentioned before, it's really gave quite a bit of comparable performance to the fully supervised. And since then, people have been really working very well. One of my current student, Kiran, usually he give this talk in here, but self-supervision is really his method. And he just actually got the news last week to get 2 of his papers accepted because he came with a new kind of self-supervision contrastive definition for certain. What he defined is when you have the geometric distortion in lenses and images, like you have the geometric distortion, any lens has geometric distortion in it. And that really adds quite a bit uncertainty to your performance, right? Because from one camera to another camera, things will be a little bit different, especially when you have quite a bit of a wide lens. So basically, he defined basically kind of intrinsic properties in the cameras to give you this contrastivity, right? And that actually gave him quite a bit of an edge of 7-8% performance improvement just because of using that, the physics of the camera into the model itself, which is I think is very decent contribution. But I just want kind of to give you this kind of I will not go through this. Just before we conclude the semester, what happens if you don't really have enough label data? Any question about today's lecture? I know there is no homework, there's no project on it, but it's good to end with that. How was the project? Hard? Yeah, if you focus on accuracy, it's very hard. Yes, yes. I think that I glimpsed through quickly. There are some innovative contributions. If we really see something that's really very nice, we may come back to you and just say basically, we recommend you to write this as a paper, but it's up to you to decide. It's not part of the grade. We'll just after the semester, we'll just let you know. There's was that nothing more than 60%. I mean, between 45 and say 55. I don't think I will be looking very carefully at the code if somebody more than 60%. I don't think it's but you should be able to get it in the 40s at least, and the 45 and above. You should be able to, but not high. Not high. It's very, very hard data. Extremely difficult. Right? I really refrain from using like ImageNet to any of these visual data because it's very easy, right? I mean, the ImageNet stuff, like natural images, right? It's with all the very, very deep network already pre-trained out there, it's not that difficult to get something very decent and saturation. But for such data, it's extremely hard. And one of the things I really want people to really think about, if you think about what I want this course students to get out from it, to know basically the very basics of what to think about in machine learning. What are the different components you have to think about, like the buzzwords, like the keyword that you have to think about, backpropagation, gradient descent. But another one is extremely important. How you deploy a machine learning is extremely important because deployment of machine learning is not like a plug and play. You have to really ask, many questions about the data that you are dealing with, the application, what you are really getting. You have to, and then how can you trust the network? What kind of different tools you have to trust the network? And we touched on explainability and certainty. These are the methods. I wish we have more time to really go deeper into these methods. But I think they're extremely important for us as engineers to kind of, when we deploy these methods and there. So that's why we picked this data, which is, I know it's very, very hard, but I think I hope the message was delivered. So we'll see. Any other feedback? Okay. Yeah, we're grading. I'm not sure when we'll finish grading, but it's a lot of appendices, by the way. Many of appendix, but we'll not go through them unless we have to. Okay. All right. Thank you for sharing your time and your career with us. I think we had a few bumps, but I think overall, hopefully it was worth it. You learned a bit, and thank you for filling out the survey. I look forward to reading them after the semester finished because I think that's extremely important, the survey. So I look forward to that. Thank you. Okay. Have a good summer.